Dark matter is one of our universe's greatest mysteries. We're pretty sure it exists, and we're pretty sure it accounts for a big portion of our universe. But we've never seen dark matter for ourselves. That could change soon, thanks to a trick with the James Webb Satellite Telescope that allows us to see dark matter. While establishing an exact map of matter distribution over the universe is a great effort in and of itself, it is especially remarkable for dark matter, which doesn't interact with light and hence cannot be detected directly with telescopes or other devices. So if dark matter is invisible, how can scientists map it? And how do we know dark matter exists at all? Simply said, astronomers seek dark matter by observing its indirect effects on gravity and how it interacts with other things with mass and light. According to the European Organization for Nuclear Research, popularly known as CERN, all galaxies are believed to be wrapped in an invisible halo of dark matter. And this envelope is critical. Galaxies are rotating so quickly that without dark matter, they would have been torn apart long ago, if held together only by the influence of their stars, gas, dust, and planets. As a result, this enigmatic material must have played a key role in the evolution of the cosmos. So what exactly causes this dark matter to be invisible? Everything we see on a daily basis is constituted of ordinary matter, also known as baryonic matter, which is made up of baryons such as protons and neutrons. Clouds of frigid gas, planets, comets and asteroids, stars, neutron stars, and even black holes are examples of cosmic phenomena consisting of baryonic matter. Because baryons interact with the electromagnetic force, one of the universe's four fundamental forces, most of these cosmic items and earthbound objects such as tables, cars, and cats can be observed. When electromagnetic radiation, including visible light, strikes baryonic objects, they absorb photons and either re-emit them or just reflect them, allowing the objects to be seen. Scientists know that dark matter differs from regular baryonic matter because the particles that make up dark matter either do not reflect, absorb, or emit electromagnetic radiation or interact with light so weakly. This means that dark matter cannot be detected using conventional methods that rely on electromagnetic radiation. Although dark matter does not interact substantially with electromagnetism, it does interact with gravity, another fundamental force. Astronomers discovered dark matter and eventually properly mapped it thanks to its interaction with gravity. The first traces of dark matter were discovered in 1933, when astronomer Fritz Zwicky of the California Institute of Technology used the Mount Wilson Observatory to measure the visible mass of the Coma cluster of galaxies. Zwicky, nicknamed the father of dark matter, discovered that individual galaxies in this cluster were moving too fast for the cluster to stay together based solely on the gravity of the visible matter. Zwicky proposed that an undetected sort of mass, dunkel materie or dark matter, may explain the discrepancy, but the concept wouldn't be generally recognized for decades until after he died in 1974. Vera Rubin of the Carnegie Institution became the next scientist to deduce the presence of dark matter while analyzing the rotational motions of galaxies, with discoveries that helped to solidify it as an acceptable feature of the cosmos. According to the American Museum of Natural History, Rubin discovered that stars on the outskirts of spiral galaxies, far from their dense centers, move as fast as stars closer to the galactic heart. This was unusual because the observable mass of these galaxies should not have enough gravitational impact to maintain stars moving swiftly in the sparsely populated outer regions. This suggested that there has to be a massive amount of unseen matter in galaxies far from dense star populations. Rubin calculated that visible matter in the galaxies she viewed must account for only 10% of their mass. And when she revisited Zwicky's findings from roughly 4 decades previously, she discovered that a similar ratio of seen and invisible matter holds together the Coma cluster. Astronomers then employed Albert Einstein's 1915 theory of general relativity to map dark matter, asserting that gravity comes from things with mass changing the fabric of time and space. This phenomenon has an impact on objects in space, energy, and even light. According to theoretical physicist John Wheeler, space-time tells matter how to move, matter tells space-time how to curve. A commonly used comparison may be useful in understanding the effect of mass on space. Consider arranging objects of varying masses on a stretched rubber sheet. The greater the bulk of one of these items, the more it warps the sheet. This means that huge cosmic objects, such as galaxies, significantly influence the fabric of space. From an astronomical perspective, the effects of dark matter can be seen everywhere, from how galaxies rotate to how light distorts around big galaxies via gravitational lensing, thanks to the James Webb telescope. If you're curious about what gravitational lensing is, think of it as this. From what we do know is that massive objects in space bend light. The James Webb telescope looks at nearer galaxies and helps scientists calculate how much they curve the light from the distant galaxies, which in turn helps them research dark matter. And now, thanks to the James Webb Space Telescope's discovery of galaxies from 13 billion years ago and novel state-of-the-art numerical models of the first galaxies, Italian astronomers have provided new insight into the nature of dark matter. Alternative possibilities advocated to solve small-scale problems of the standard scenario rely on the hypothesis that dark matter is composed of warm particles with a small, non-negligible thermal velocity, referred to as warm dark matter. The prevalent paradigm of structure formation is based on non-relativistic matter that interacts only gravitationally. Dr. Umberto Maio, staff researcher at the Italian National Institute of Astrophysics, Astronomical Observatory of Trieste, and lead author of the paper describing the discovery, published in Astronomy and Astrophysics, said that they found that the recent JWST galaxy detections in the first fraction of a billion years after the Big Bang are precious probes of the nature of dark matter. According to the results, cold or pleasantly warm particles with masses higher than 2 keV make up dark matter, the major ingredient of matter in the cosmos. From this, the study rules out dark matter models with particle masses below this threshold. Using ancient data and sophisticated numerical simulations, the authors of the most recent study were able to shed light on the fundamental properties of matter. Previous investigations were unable to differentiate between dark matter theories using modern data. The team used the most recent JWST data along with a newly developed high-fidelity numerical implementation of early galaxy formation to analyze the statistical behavior of primitive galaxies and differentiate between competing models. Dr. Umberto claims that the mass of dark matter particles determines the observable characteristics of cosmological structures during the time when the earliest stars and galaxies develop. The most recent JWST data can be used to compare the different dark matter theories' predictions for cosmic star formation, ultraviolet luminosities, and molecular abundances. The study paves the way for a deeper comprehension of dark matter and its function in galaxy formation and evolution. Uncovering dark matter's composition and behavior in the universe will require a combination of observable data and complex simulations. Aside from this research into the nature of dark matter, Jamie Farnes, an astrophysicist at Oxford University, has proposed another theory that may finally solve the long-standing mystery. Farnes proposes that dark matter and dark energy coexist as a dark fluid composed of negative masses with negative gravity, pushing objects away rather than pulling them towards them. Barnes's theory, which was published in Astronomy and Astrophysics, aims to explain some of the universe's strange properties, such as how galaxies spin so fast that they should rip themselves apart. However, dark matter halos prevent such devastation. The search for the true nature of dark matter continues, with researchers investigating various theoretical frameworks and conducting experiments to shed light on this enigma of the cosmos. Scientists are getting closer to understanding the fundamental fabric of our universe as they delve deeper into the mysteries of dark matter.